So inside a multiprocessor.
Question from UCLA.
Yeah.
Is it possible that two warps can update the DRAM, a single DRAM memory location at the same time? Write into DRAM? Can two warps do it at the same time?
Can two warps write into the same DRAM location at the same time?
Yes.
Well, there's a couple ways I can interpret that. If they're trying to write, say, to the same byte location, if you're not using atomic operations, you don't know who wins the write.
Yes.
So you need to use atomic operations to ensure that you maintain ordering and you don't lose data. But we don't protect you from stabbing yourself.
Okay. Thanks.
Sure. Okay. And by the way, these are all great questions. Thanks for asking. It's really good.
Can I have a question, Georgia Tech?
Yeah.
So the question is, for the systems with multi-GPUs, are there any plans to allow for the transfer between two GPUs, but without going through the CPU? Somehow maybe like a special dedicated PCI Express, I don't know.
Yeah, so
control from CPU, but without avoiding, the.
So I think that's a very good question, and it's a problem a lot of people see when they're trying to build bigger systems with multiple GPUs. And I think I would have to say that plans is perhaps a strong word, but there are hopes. And there's no technological barriers to what we would call this is peer-to-peer transfers across the PCI Express bus. And in fact, we do have technology in the process of being rolled out for high-performance computing that allows peer-to-peer transfers between InfiniBand and GPU without going through the CPU and without going through the system memory. But it requires a very tight lockstep between the driver and the hardware and synchronization between different devices. And with non-GPU devices that NVIDIA doesn't make, like network cards, we have to interact with every manufacturer and every driver. Even with our own, we have to build the driver stack so that someone else can be writing in your memory. Right now it's single access, so you don't have to worry about anybody else writing into the GPU's private memory. So that's in process. We're working on it, but as I say, I think using the word plan to describe it is a little strong. But I think over time that capability will exist. Okay. So the multiprocessor. The Fermi multiprocessor can handle up to 1536 concurrent threads, and that's for each multiprocessor on the chip. And each multiprocessor has 32K 32-bit registers. And again, that sounds like a huge number, but then you divide it out by the number of threads that can be running, and it begins to feel a little more constrained. If the multiprocessor is not fully populated, you can have up to 63 registers per thread. Even if you only have a very small number of threads, you can't have more than 63 registers because that's the indexing that we have. That's the number of bits that we have. If the machine is fully full, if you have 1,536 threads occupying the multiprocessor, this drops down to 21. And it drops down smoothly, so however many threads you have divided by the number of the integral number of registers that you get by dividing it out is how many you get. The functional units in the SM, we have very high instruction throughput on Fermi. There's 2 FP32 pipes, 2 INT32 pipes, 1 FP64 pipe, and 1 SFU, special function unit. And the latency and throughput of each of these is basically targeted toward what we see as the use pattern. So this is something that can change from implementation to implementation to change the performance balance. For instance, Fermi has much higher double precision floating point throughput than the previous generation, but it's actually balanced in terms of data flow. If you look at the size of 32-bit operands versus the size of 64-bit operands, if you had the same functional unit throughput for both 32-bit arithmetic and 64-bit arithmetic, you'd be wasting something somewhere. So that the 2-to-1 ratio actually balances the data path. So you can issue instructions to multiple pipes, and in this implementation we have true dual issue. In previous generations we had the capability of issuing 2 instructions, but there were enough special cases and conflicts in our architecture that very rarely could you actually deliver dual issue. In the Fermi architecture, we can almost always deliver dual issue. We can run 2 instructions through each multiprocessor per cycle. And the way we do that is we issue instructions from 2 different warps, so we've guaranteed that they're independent, to 2 different pipes in the execution unit. And so it's very, very easy for us to find. Those are the only constraints, so it's very easy for us to find something that can be issued most of the time. Okay. It's really the way to think about this machine is it's all about throughput. So if we can consume 2 instructions per cycle per multiprocessor, we can get the peak performance, as long as we can issue them. So the memory and cache of the multiprocessor, there's 64K of L1 cache or shared memory in the Fermi processor, and I say or because it's actually the same physical devices, and we've added the capability to choose whether you want more shared memory and less L1 or the other way around, because different applications work differently. There's 32 banks of shared memory, 32 bits wide, and this is an improvement over the last generation, which had 16 banks. And we also have gradually improved the usability of the shared memory, adding features such as multicasting. So previously you could only have broadcast where all the threads in a warp get the same data. Now you can have say 2 pieces of data, and some of the threads get one of them and someone gets the other, but that can all be one cycle as long as there's not a conflict. And so there's no bank conflicts at all now for either 64-bit or 128-bit accesses. So this is, at a high level, the way to think about this is over time we intend to make the performance cliffs and the sharp edges softer and gentler, so that if you don't arrange your access exactly correctly, you don't pay such a big penalty for it. In previous generation of hardware, if you did misaligned or conflicting accesses, again, you could run 32 times slower for that access, but now the hardware helps you a lot with that. So the L1 cache, if you remember the diagram on the second slide, the L1 is part of the SM. It's not part of the global memory system. So it's local to the threads within that multiprocessor. The cache line size is 128 bytes. And again, that may seem like very large, but that's for 32 threads. So that's really only one data value, one 32-bit data value for threads. You can choose a path where you have smaller access granularity, but it will pass right through the cache. It won't, your accesses won't get stored in the L1 cache. And the case where you would want to use that is where you know that you're not going to get any reuse. You know that you're not ever going to get another cache hit for that data. So you don't want to pollute your cache with a value that is only going to be used once. And again, there's a lot of cases where people want that. And L1 is not coherent until it's actually written out to the external memory. It's only coherent within the single multiprocessor. I have a question here.
A few moments ago, you mentioned that the L1 is not a true cache, that after a few cycles it's cleaned out. So I presume it remains a true cache in the lifetime of the warp, or how would you explain that?
Well, okay, so I should say it a little more clearly. It is a true cache, but it doesn't end up behaving the way you probably expect a cache to behave on a CPU, because it's so small compared to the traffic. You don't have a long lifetime. We don't explicitly purge it, but it just happens that way. So the cache, the data that you're accessing, you're not addressing them in the cache. You're addressing them by their global addresses, right? So when they get written out, they get written out. So I think the question you're asking is your data going to get trashed during the lifetime of the warp? It's not going to get trashed, but it might become slow again if it gets demoted down the hierarchy. But it won't get lost.
So a follow-up, but maybe you can repeat this. So from the application user standpoint, are there ways to address explicitly whether it is shared memory or L1 or variations thereof?
Yes, from the application point of view, you designate.
Question.
Huh?
Repeat the question,
okay,
since we didn't get him a mic.
Sorry. From the application point of view, is there a way to specifically designate whether values are in shared memory or an L1? And the answer is yes. If you want something in shared memory, you have to say it's in shared memory and you have to put it there. If you just access a global memory address, it'll be presented to you through the cache hierarchy through L2 and L1. So that's one of the reasons that shared memory is so valuable, is that you can guarantee performance with shared memory, because once you load something in shared memory, it stays there until you write it out.
Michigan has a question. Hi. So the L1 cache and the shared memory, do they have the same like memory bandwidth? Because of basically they are the same physically.
Yes.
Okay, thank you.
Good question. I had to think about it for a second, but I'm not absolutely positive, but I can't see any reason why that would be different. There may be another cycle or two of latency for the tag check and all that, but it doesn't show up. You don't see it. It gets hidden by other things that happen.